All right, well, happy Friday. We survived another week, and and anyway, so uh, oh, let me turn these lights on. Okay, so last Friday I introduced this substitution cipher thing. Okay, where you have the letters and we've scrambled the letters up. So these 26 symbols got replaced with some other letter, and you've intercepted some kind of message and you want to decode it. That's kind of where we are. So we're going to say we want to decipher a coded message. This is going to be the coded message that we've encountered. ZTRZY, EKXHZR, EKXRBs, NZ, BYTBR, RB, NZ. And then we want to go, okay, well, what is this? What was the original message? And so all we know, or we're assuming, is that the original message was kind of created, or coded into this using a substitution cipher. So there was some original message, and then somebody used some kind of key letter mapping, and it turned the letters into this. And we want to take this message and decipher it, okay? And so we have to figure out, okay, what was the original letter mapping that we had? And if we had that original mapping, then we could get back the original message. That's what we want to try to figure out. But we don't know. We don't know what the original thing is. So, but this is kind of the way it's going to work. If I said, hey, this was the original mapping, or I said, okay, or I don't know, let's say you found these different, I don't know, you found a book of code, like a code book or something, right? So this was a thing like in World War II. Well, they had like fancy machines, right? They had like the Enigma machine and things like that. But then one of the kind of valuable possessions was the code book, and they were often written in water-soluble ink, so that like if they knew they were going to get captured, they just throw it in the water, and then you couldn't read it anymore. But the code book would have like different pages of potential codes that could be used or something. And so let's say you came across a code book or something, and you had this, and you said, well, I wonder if this was the key code that they used. And if you apply this to this thing, and you say, okay, we got back a Z, okay, so that means the original letter must have been a K, and then we got back a T, so the original letter must have been a B, okay? So on and so forth. If you do that, then the original message would have been this: KBDKE OQFAKD or something, right? And then we go, okay, do you think this was the original message? And we look at this and we go, nah, I doubt that this was the original message, okay? Because just our instincts, we look at this and we go, well, that does not look like it's legible or understandable or intelligible or anything like that, okay? But rather than just kind of going off of gut feeling about like, do I think this was the original message or not, we want a way to kind of evaluate this a little bit more methodically, and so we use Bayes' rule, okay? And when we talked about Bayes' rule, okay, basically we want to figure out what is the posterior probability. We want to know is what is the probability of this cipher key mapping given the text, okay? So we want to evaluate the probability that this was the original text. So using Bayes' rule, we stated that the probability that this is the correct mapping, okay, given the text, is proportional to the likelihood of the text message given the mapping, okay? So we said we want to figure out what's the probability that it was the mapping given the text. That's kind of the data that we have. the mapping given the data, the text, and that's going to be, using Bayes' rule, we say, well, that's going to be equal to the probability of the text given the mapping times the prior probability of the mapping divided by the marginal probability of the text, regardless of the mapping, okay? But we said we have no prior beliefs regarding the mappings. We have no reason to believe that one particular scrambled key is more likely than another, so this is a constant. And then the marginal probability is always a constant. So we have a constant and a constant, so we can just say that this thing is going to be proportional to this thing. So this is kind of where we are. We said the thing that we're going after, the probability of the mapping given the text, is going to be proportional to the probability of the text given the mapping. And so we just need a way to evaluate what is the probability of the text, and that will give us something proportional to what we want to figure out. So when we talked about what is the probability of the text, there were two things that we are going to use, okay? One is we're going to look at the two-letter combinations, okay, found in the quote-unquote original text. So once you apply the key and you get back this text, we'll say, hey, does this look like it could have been the original text? And we look at the key combinations, right? We look at, okay, KB. How often do you see the letter K followed by the letter B? And I'm thinking like, I don't know, backbone or something like that, okay? So that might be an example where you have a K followed by a B, okay? And what about a B followed by a D? I'm sure there's words. Would it be B's followed by D and a D followed by a K? I don't know. They're not super common, okay? And we have that kind of mapped out on this. We created this mapping by scanning like the big text of War and Peace, and we looked at every single letter combination we saw there, and we tallied them up. And we said, hey, you know what? Certain letter combinations like H followed by E are very common, and T followed by H is very common because that appears in the word the, TH and HE. What do we say? K followed by B? Okay, not very common. It's like very light. K followed by E is reasonably common. What was the other one that we saw? B followed by D. B followed by D. Again, not very common. B followed by E is a lot more common, but B followed by D, not very much. Okay. Other letters, C followed by H, and what is this? H followed by I, H followed by O, H followed by T is actually common. So anyway, well, we use that as part of our thing, okay? And then the little party trick I showed you was on the touchscreen keyboard on your phone kind of employs something like this, where after you hit the letter T, the area of your screen that gets mapped to the letter H gets bigger, and you know, after you hit N, the area of your screen that gets mapped to G gets bigger because of just the way these things are set up. And so you can hit the same spot on your screen and you'll get different letters. Okay, so that's part of the way we're going to calculate it. And then the other part that we're going to use is we're going to, once we start seeing real English words, okay, or if we see real English words in our output, that's going to be a good sign. And so we've loaded this, we have a data thing. Let me okay, we load up this lexical database. And you can see it's just got a whole bunch of different words, and it has like different relative probabilities. Abandoned is more common than abandon, which is far more common than abandonedly and abandonable. Abandonable. I'm trying to think of a sentence that uses the word abandonable. Okay, I don't know. This job is abandonable. I don't know. All right, and then I don't know. I have no idea what this word is. Abasia. Okay, so apparently that's a word. It's 1.17 times 10 to the minus 8. So this is just something. I think I downloaded some of these probabilities off of. I think Wikipedia had some kind of thing on there, the words. So anyway, we have that, and basically we have a function that you put in a word. So I type in 1 gram probability, and I think I put in the word like hello. Oops. Oh, I have to provide it the lexical database. What is it? Okay, word, and then we want to look at lexical.database. All right. And so the probability of the word hello is 6.424 times 10 to the minus 7. What do you think is more common, hello or high? Higher or lower? Or on the same order, 10 to the minus 7. Huh? Lower, less? Let's see. 10 to actually more probable, 10 to the minus 6. So about high is more common than hello. What about goodbye? More or less common than hello? Gotta be less common than hello, right? Oh no, it's more common than hello, but less common than hi. What about just plain old bye? More common than goodbye. More common than hi. Bye? 3.5 versus 1.5 times 10 to the minus 6. I am amazed. Okay, I don't know. So anyway, you can put in these things, and you will get these probabilities. And basically, all this does is it just looks up the word in the lexical database and gives it back. Okay, but I've also just to avoid problems again, if it can't find something, like if you type in the gibberish, KBDB, whatever, okay, and it can't find it, it's going to just default to giving a very small probability, but not 0, because 0 probabilities cause problems, okay? 0 basically means it's impossible to get this thing. So, so we don't want to say that it's impossible, okay? And then we have this thing, which will basically, so when you are working with really small numbers, like 10 to the minus 6, 10 to the minus 7, you're gonna, and you have like, you're taking products of these things, you're gonna quickly run into the limits of floating point arithmetic, because you can represent really small numbers, but what was, I don't know, machine epsilon is on the order of what, 10 to the minus 52? No, okay, well, that's not helpful. Okay, or 2 to the minus 52, maybe. Yeah, okay, so this is kind of our machine epsilon. And, we quickly run into problems. And so generally we want to switch to logs, okay? So if I have, if I'm looking at by, I want to kind of feed that into log, and we'll turn it into something like negative 12.55, okay? And here, this function of log probability words will take in a string. So if I type in by and I give it the lexical database, okay? It will give us basically the log probability of the things. And then if you have multiple words, like if I say bye-bye, it'll treat this as, what's the probability of this? And it's going to treat each word as independent, and we'll get kind of like the probability of this followed by the probability of this is something like that, okay? Versus, you know, so the longer sequence of words that you have, the more negative it's going to be. So if you have like, what is the probability you got hi, bye, and hello? It's going to be the sum of basically the 1 gram probability of hi, converted into a log, okay? Hi, bye, and hello. And so all we're doing is we're just taking these things, and I'm just, if I do negative 13.37 and add on negative 12.55 and add negative 14.258.376, and I add these up, you know, I get this number, negative 40.18, okay? Negative 40.18. So that's basically all it's doing, is that when you give it an entire sentence, okay, it looks at the spaces, it separates them out. Once it isolates each individual word, it looks up each individual word, turns it into a log, and then adds them up, okay? So it's kind of, does that kind of make sense what this function is doing? So because what we want to do is we basically want to figure out, you know, what's the probability of this whole thing, okay? So it's going to take this entire string, it's going to break it up at the spaces, look them up, and, you know, when it can't find the words, right? So here my thing says hi, bye, hello, but if rather than hi, bye, hello, I had gibberish, 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 okay? So if I have da, 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 and, you know, gibberish, 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 it's going to come back and say, I couldn't find any of these words, and so the log probability there is negative 69, okay? Because when you just look up one gibberish word, okay, the log probability of one gibberish word is negative 23. So if you have 3 gibberish words, you know, it's going to be 3 times that, negative 69 there, okay? And obviously, when you have real words, your log probability is going to be much less negative, okay? And so so we have a way to evaluate kind of the probability of these things. So so we're going to add those two things together. We've got the probability of the 2-letter combinations. We're also going to add in the log probabilities of those real words, okay? And we have some kind of scaling factor, okay? So this is how we're going to evaluate our probabilities here. Oh, okay, let me give you your first view quiz answer, which is the letter D. D as in dog. Okay, and this scale thing, okay, so the probability, or I should say the log probability of the text is going to be the log likelihood of our 2-letter combinations, and then we're also going to look at the log likelihood of the words multiplied by some scaling factor. And the scaling factor is going to kind of decide which of these priorities are more important, right? If you have a bigger scaling factor, then it's going to say anytime you find a real word, that's going to be like huge, versus, and then the 2-letter combinations don't matter as much, versus if you have something really, really tiny, it's going to say the 2-letter combinations. Like the extremes would be scale is 0 on this, and that means only the 2-letter combinations matter. And then the other is scale is this like infinity or something, a really big number, and basically means only the words matter, okay? Naturally, the value here is actually going to be kind of small because the log likelihood of words is going to be very negative, because like the most common word, the, its log likelihood is still pretty negative, okay, at negative 2.877. Okay, and that's just because there's around 80,000 words in this dictionary. So even if all 80,000 words have equal probability, which they don't, each of these words would have a really kind of small overall probability, right? 1 over 80,000 type of thing, okay? Whereas when we're talking about our two-letter combinations, there's only 27 by 27, 729. So each two-letter combination is going to be 1 over, if they were all equally likely, which they're not, but if they were all equally likely, they would on the order of 1 over 729 versus when you're talking about the words, they're on the order of 1 over 80,000. So in reality, it's even smaller, like 10 to the minus 6, 10 to the minus 7 or minus 8 for some of the words. And then, you know, for our two-letter combinations, I don't know what this, our transition matrix, I don't know what the, our two-letter transition probability matrix, what's our max value? Okay, the largest is around on the order of around 0.036, 3%, and then the minimum value is on the order of 10 to the minus 7. But that's like if it found none of those letter combinations. Okay. All right. So how are we going to find which is the correct key mapping? Okay. And again, if you think about all of the different possible letter mappings there are, cipher key mappings, there are 26 factorial on the order of 4 times 10 to the 26, just a ridiculously large number, and it would be incredibly inefficient to just simply randomly try a mapping and then evaluate its likelihood. Like, that's just not going to get us there, right? Because if we try that, the probability of hitting a good mapping by random chance is very low, okay? And so just kind of illustrate this, I just created 3 random mappings. I said if this is the original text and this was the mapping, if this is the coded text and this was the mapping, then the original text that creates this coded text would have been this. And if this was the mapping, this would have been the original text. And if this was the mapping, this would have been the original text, okay? And if you look at these, right, the original text for this KBDKE, OQFAKD, that's nonsense, okay? GKNGV, EHBUGN, also bad, KFPKM, WQATKP, okay? These are all junk. It feels like we're not making any progress at all. It feels like there's no way we're going to be able to find a good mapping, okay, with this kind of approach. So what do we do? This is kind of the power of the Metropolis algorithm, okay? I don't know if you recall, the Metropolis algorithm, I did an example where we were trying to generate values from a normal distribution centered at 15, but I had the starting location at like 100. And it eventually found its way to kind of like the right location, okay? And so that's what we want to try to do. We're going to just start off at a random location, which we know is like, if it's one of these 3, all of these are bad. We know if I just start off at a random location, it's going to be terrible. But I just need to take small increments, even if the incremental step I take isn't that much better. If it's just a tiny bit better, that's great, okay? As long as I can kind of get tiny bit better, if I take a whole bunch of tiny bit better steps, eventually I should get to where I want to go, okay? And so that's what we're going to do, okay? Instead of just taking a completely new random mapping and just saying like, okay, well, this was bad, let's just try a new location, okay? We're going to just start off with this really bad, okay, really bad mapping, and then I'm going to just say, hey, I know this is really bad, but can I make it a little bit better? Okay, can I make it a little bit better? And the way I'm going to propose making something a little bit better is I'm going to just say, what if I just swap 2 letters? Okay, so this is my current mapping, it's bad, but what if I just changed 2 letters around and see what it produces? Is that incrementally better? Okay, so this is a contrived example, but let's say, okay, so this is our coded text, this is my current mapping, and if I run this thing through the current mapping, this is what it produces, okay? And I'm going to switch the letter B and the letter E, okay? So right now, this word RB, okay, translates, the original text would have been DG because G becomes B, all right? And then R becomes the letter D, okay? And B becomes the letter G. So this word right here, whatever it is, RB becomes DG, okay? And then, but if I swap what B and E are assigned to, okay, then now G gets turned into E and O gets turned into B, all right? And so if the original text was RB, okay, then B gets turned into O, and so the word this 2-letter word becomes DO. Okay, and so if you look at these two, compare these 2 mappings, all right? So a lot of these words are exactly the same. We still have KB DKE, KB DKE, okay. But instead of OQF DG CKGE, we have GQF DO CKOE, okay? And instead of BGD, we have BOD, DG DO, right? And so if we look at this is still complete gibberish. But we might say this one is just ever so slightly better than this one because some of the letter combinations are a little bit better, right? Like it's more common to see D followed by O than it is to find D, well, I don't know. There's a lot of words where D is followed by G, like judge and bridge and things like that. But, you know, there's also a lot of words where D is followed by O. And as far as like actual words that appear, the word do, like that feels like a good sign, okay? And then certainly things like BGD, that doesn't feel like it's a real word, versus BOD, and probably this wasn't the original message where somebody's talking about a bod, but this text feels a tiny bit better than this text, okay? And so when you plug this text into our functions, the log probability that it calculates is less negative. Okay, so the log probability of this text is negative 1,807, and the log probability of this text is 1,788. So we'd say, okay, this is a step in the right direction. And so so we will take this, okay? And this is the idea, is that I'm going to just propose, okay? So remember the Metropolis algorithm, you start off at your current state, you propose some place to go to, okay? And you look at, if I propose this location, is it any better or not? If it's better, you go there, okay? If it's not better, you go there probabilistically, okay? If it's only a little bit worse, you have a decent chance of still going there. If it's a lot worse, you have a very low probability of going there, okay? That's how the Metropolis algorithm works. And so you know, we started here. And so again, you know, states are a little bit of a weird thing when you have this, I don't know, your state space is this, you know, high dimensional space of 26 factorial locations. But we're going to propose a new location, okay, where I just swapped 2 letters. And I say, hey, does that look any better? In this case, I proposed swapping the B and the E, and we look at the log probability and it got better. So we say, yes, let's take it, and we go there. okay? And then so now this is going to be my current state. I'm going to propose swapping 2 other letters, okay? And maybe if I swap those 2 letters, it gets worse, okay? Or maybe if I swap the 2 letters, it gets better, okay? If it gets better, we'll go there. If it gets worse, maybe we'll go there, maybe not, okay? If it gets a lot worse, we won't. We probably won't. But if it gets, you know, a tiny bit worse, maybe I'll still check it out, okay? So that's how it's going to go, okay? So, you know, you do probability of the proposed divided by probability of the current, or if you're doing log probabilities, you do log probability of the proposed location minus the log probability of the current, okay? So you do a difference rather than a division if you're dealing with logs. And basically, if you get something greater than 0, you'll go there because that means your proposed location is better or has a less negative probability. Okay. So we're going to do, normally we would do random U. If the random U is less than P proposed divided by P current, we'll go there. For the log version, it's going to be log of U. If that's less than log of P proposed and log of P current, we'll go there, okay? And so here, rather than just trying a true random sample, we're just going to take our current thing, take 2 letters, swap them, and we'll just get small incremental improvements. And if we can just do small incremental improvements, we can kind of trust the Metropolis algorithm to kind of eventually get us to where we want to go, okay? So what did I write? This is great because we build off previous states. If we just did true random sampling, we have a 1 in 26 factorial chance of ever hitting the correct mapping by random chance. Instead, we take our current mapping, propose swapping 2 letters. If the letter swap results in a better map, the Metropolis algorithm will accept it. If it results in a lower probability, it might accept it. And it will naturally gravitate towards areas of higher probability, even if you give it a poor starting location. Okay? Now, technically, this deciphering thing is more of an optimization problem because what we're looking for is we're trying to find like something that's going to give us the maximum probability of the original text. And what we're looking for is the letter mapping that maximizes the probability of the original text. Whereas when we think about the Metropolis algorithm, it's usually used to produce random samples from a distribution. So why are we using the Metropolis algorithm here? Okay, the Metropolis algorithm still works because it's effectively searching this state space, which is huge, 26 factorial possible states or possible mappings with different probabilities, and it's naturally going to produce samples after the burning period. It's going to produce samples from the areas of high probability. Okay, so while it's not a strict optimization algorithm, it does have the effect of being able to start at a terrible location and then finding its way to areas of high probability. Okay. Now, when you do the algorithm, sometimes it can get stuck in areas of a local maximum where the current mapping is still kind of terrible, but all of the proposed letter swaps result in even worse mappings. And if that happens, you might have to kind of restart the chain at a different location. But that's that. Okay, so are we ready to try this out? So we have log probability of the words. Okay, so here I'm going to take, I just have just some kind of random mapping here. And I'll try feeding it through kind of my current decoded text. And so if I feed my encrypted or ciphered text through it, it gives me this, still total gibberish, okay? And the current kind of evaluation of this thing is negative 905, okay? Oh, actually, no. The combined likelihood, okay. the current evaluation is negative 1,780, okay? So this is kind of where we start. We're looking at this and we're saying this doesn't look good. Its evaluation is negative 1,780. And what we're going to try doing is we're going to try different letter swappings, okay? I'm going to keep track of kind of like what my best decoding is and what my best score is, the least negative of these things. I'm going to run up to 1,500 algorithms, 1,500 iterations. We probably can stop before that, all right? And what we're going to do is I'm going to just select 2 letters at a time. So my proposal is I'm going to say, okay, let's swap letter 4 and letter 13. So what? The letter D and the letter M. I'm going to try swapping those. So my current mapping, my current mapping is this, and I'm going to try swapping the 4th and the 13th letter. So I will take this, and if I do that, my proposed mapping is very similar, but all I've done is I've swapped the 4th letter and the 13th letter. So N gets swapped with W. And then we're going to try, okay, well, what will the text be if I decode this, okay, if I use this thing? All right, so my current decoded text versus my proposed decoded text. Okay, this is my current decoded text, and if I swap the letters N and W, what happens, or I don't remember, D and whatever, okay? So again, is one of these things better than the other? We have M and W, so MI becomes DI, HD becomes HM, WHD becomes WHM. Are either of these better? Well, we can plug it through here and we can see what this score gets. Okay, so the proposed score is negative 1,764 versus the current score is negative 1,780. So the proposed is, even though it's hard for us to tell as humans, according to the machine, the proposed location is better because it has a less negative score. So we would accept it, okay? And we would go on from there, okay? So, all right, so let's try this out and let's see how it works here. And let me, so my challenge is if you can identify what the original text is. It is a famous quote. I guess that will be the clue, all right? So if you can identify this famous line, all right, so it starts off here, and basically every time, so it's not printing out every single thing, but every time it accepts a swap, it will print it out. Okay, so we're at, and it might get stuck. I don't know. I hope this works. I probably should have set a seed to make sure like it will work out. Okay. All right. So we are at iroid whoop pio woo on c and ernon on c. Okay. So this doesn't feel like it's anything. It is. So it's stuck here because it's like proposing letter swaps, and then all of those letter swaps are being rejected. So when it gets rejected, it's not updating anything on the screen. Okay, now we've switched something, and now we're at Eroes, Wamio, Ereas, Humia, Hu, and Des, and RNA, ANDA. Oh, it might get stuck. I don't know. So, I mean, we went from total gibberish into still gibberish, but this at least feels English-y, or at least like some kind of language, because we see vowels, right? Like we see at least the constitution of these words feels like it could be words, right? In that it feels like, okay, it's not English, but it feels like it's some kind of language where we understand that there's vowels. Oh, I hope we get something. Just ran out of It's not working. Yeah, sometimes it gets stuck, and you might have to like start the chain again. But I don't know. I'm hopeful. I've got about 5 or 6 minutes for this to run and see. Okay. Let me try starting at another random location because I feel like we're getting stuck and it hasn't changed too much. So let me try pausing this. Okay, and let me just try running it again. So sometimes that could happen. Hmm? It is. I don't know how you figured that out.
I got it after like about 180.
Oh, okay, you ran it on your own computer. Okay. Yeah, let me. All right, so you're running yours, and yes. Okay, so here I just started another thing, and seems like it's working. But we'll. So you said you got it around 180?
Yeah.
Okay, let's see. Here, at 70, 80, yeah, okay. Yes, it is. It is from Hamlet, and then, okay, we're kind of getting there. So the first line is going to be enter Hamlet, and Hamlet says to be or not to be. That is the question. Let's see if we can get there. Right now we're at Ayrton. Ayrton Hadwet had to be on rot to be that. Psst, the Westpor. Okay. Ayrton Hadiyet had to see on rot to see. So, Hamlet, yes. Okay. The famous line is, "To be or not to be." He's contemplating. Well, I don't know. Spoilers here. His father's murdered by his uncle, and then and he sees this. He encounters his father's ghost, and then he's deciding, like, what to do, and he's actually contemplating, like, suicide and ending it all. So he's asked, he's wondering, to be or not to be. Okay, oh, look at this. Enter Hamlet, ham, to pee or not to pee. That is the question. Oh, there we go. To be or not to be. That is the, question with a C. And we forgive that question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or and it should be to take arms against a sea of troubles and by opposing end them. Okay. Well, that feels good. All right, it worked. Yay. Okay. But yeah, sometimes you start off at some location and it will get stuck and it will just produce kind of gibberish and things like that. And you might have to kind of do some adjustments. But here it seems like it has kind of gotten us at least to a location of higher probabilities. Remember, the Metropolis algorithm isn't an optimization algorithm directly, but as a sampling thing. So it's producing, okay, there we go. To be or not to be, that is the question. Okay, and we have tave arms, and I don't know if it will ever, by random chance, switch the V and the K to give us the kind of the thing. But right now it's, okay, and then, other high probability things are C's and K's, question of things here. Okay, so I'm gonna go ahead and just hit stop there, but I feel like we've had success in running the deciphering algorithm here. Okay, I'll give you your last two view quiz answers, which are the letters A and D. A is your second answer and D is your third answer. All right, that's it. Have a good weekend. We'll see you next week.